Okay, good afternoon. Good afternoon, everyone. We're going to get started. I appreciate everyone making it out today. My name is Michael Joy, and I'm the teacher of the capstone course here at Twin Valley. And there's a few people I'd like to thank before I turn it over to the students. First and foremost, our jury up front. We really appreciate you coming out to support the students, take time out of your schedule to give them feedback and see the things that they've been working on. Did I hear something back there? So I appreciate that. I'd also like to thank our district administration for their support, Dr. Please, Dr. Sequoian, Mr. Clements, Mr. Barber, and Mrs. Edwards as well. I'd also like to thank my colleagues within our department. They certainly had a hand in getting the students to this point, and also for the rest of the faculty here at the high school, really have all contributed to getting the students getting ready to graduate at the end of the year. So I'd like to express our thanks to them as well. So they've worked very hard this semester, and without further ado, I'm going to turn it over to Evan, and he's going to talk a little bit about the course, the presentations, and then they're going to get us started. Thanks, Evan.
Hello, everybody. I would like to officially welcome all of you to this year's Engineering Design and Development presentations. So Engineering Design and Development, or EDD, is the capstone course here at Twin Valley for all our engineering classes. So as I said, the capstone course enables students to experience the engineering design process, where our students are required to identify, justify, and solve a relevant problem. So through designing, building, and testing, and evaluating a viable solution. So just a couple things before we move into the presentations. The presentations are 15 to 20 minutes long. There's going to be 3 presentations, and we ask that the presentation jury please fill out 1 evaluation per presentation. And we ask again that you please hold all questions towards the end, because there will be an informal 30-minute question-answer period after all the presentations are finished. So moving into our presentation, allow me to introduce myself. My name's Evan Lawler. I'm part of Horse Engineering, and our product is the Clean Machine. These are my teammates, Ben Dayton, Aaron Crum, and Gavin Whitlatch. So the problem statement that we first identified in the very beginning is that 25.6% of shower towels are contaminated with coliform, which is a digestive bacteria which thrives on bathroom towels in large part of the damp, warm environment of a bathroom. So this was our Gantt chart, which we set up at the very beginning of the year. It was basically just our planning tool to make sure that everything was taken care of and got us to this point. So for example, some of the first things were brainstorm ideas, whittle down those ideas to our top idea, our problem statement, and then finally the last thing on the left side there is the presentation. So our problem justification, after we decided on our problem statement, we sent out a survey to the school, and we actually got 129 responses from both students and teachers, people that we identified as users and the students, and then the people that would actually be purchasing the project would likely be the teachers. So we got those results, and on the left side there it says, would you consider purchasing a product that rids your bath towel of bacteria after each use? And we found that 90.7% said yes. And on the other side there we have how often do you shower weekly? And the yellow, the largest portion, was 74.4%. So we found that this is an extremely relevant problem, and we thought that that justified us moving forward with this problem statement.
All right, hello again. I'm Ben Dayton. As Evan said, we worked with the surveys, sent it out to a bunch of people, and afterwards we needed to figure out how to actually design a product. So the first step we did was the similar solution matrix, and we basically we took 5 patents and 3 already existing products, and we graded them individually, and then we compiled our results at the end. And we found that the towel spa was victorious. We got a 38.75. And the towel spa was basically an enclosure that the towel sat in, and it was in contact with ultraviolet light, thus disinfecting the towel. So 2 other solutions that already exist. This one on the left here, it didn't actually have a name, so we just called it the hoop. And it works with the towel sitting on the rack, and then the UV light just shines on it, ridding it of bacteria. The other product The towel sits on the bar, and then it is hit with fans from both sides, thus ridding it of bacteria. We like both of these designs, but the one thing that we did not like about either of them was that it was not enclosed, so it was still, airborne bacteria could still go on the towel. So previous patents that we found, the one on the left here, it's mounted on the wall, much like our design. It works by the towel. It goes down through and is eventually in contact with a cleaning solution that cleans the towel. The one in the center is kind of like the towel spa. It's a container that you just open up and you stick your towel in it, except it's just heated. It doesn't really get rid of bacteria. Again, on the right, it's just more heat. It's just hung on the wall. The towel is weaved in and out of it, and that's how it's disinfected, is dried. So after we did that, we had to come up with designs of our own. So the first activity we did was the 12 sketch activity. So for homework, we all had to come up with 12 individual sketches. And like the first one here on the left, it was our first design, and it was just basically an enclosure that contained heat bars inside and UV lights. On the right, it was kind of similar. The design was kind of similar, except it had rollers on the inside that the towels rested on, and it did not have heat. So the next activity that we did for brainstorming was the draw and pass activity. So we got in our groups, and each person started a design. From there, we took 5 minutes, drew our design, and then passed it. Once we passed it, we took another 5 minutes, and each person would add something to the design to help further enhance the solution. So here's just two of the 4 that we did. So the next thing we did for brainstorming was the mind map. And Evan's holding it up because this picture quality is not the best here. But what we basically did was we branched off into 2 pairs, and we drew a central idea. So for this idea, it was like a cabinet. And from there, we added different aspects to it. So this is where we kind of got into, should we use UV light? Should we use heat? Should we use this? So we did decide that we wanted to use a UV bulb. So we had to do research on it to determine which one we needed. So we found UVA, UVB, and UVC. UVA and B were both too powerful for what we needed. So we decided that the germicidal UVC bulb would be the best for our solution. Some more research that we had, we found that germicidal UVC lamps kill up to 99.9% of all bacteria. So it's pretty good for our solution. We also found that many bacteria can survive for extended periods of time without moisture, but without it, they can't grow or reproduce. So this is where we kind of got the idea to use maybe an exhaust fan. So that's what we went with, and we added an exhaust fan on the top, so that way it ridded the box of moisture, thus the bacteria cannot grow. Another piece of research that we found was that E. coli is present in your bathrooms at all times. No matter how clean your bathroom is, there's been tests done to show that bacteria will still be airborne and still come in contact with your towel. So after that, we went to the decision matrix once we kind of had a feel of what we actually wanted to do for our prototype. And so we had different specifications that we wanted to kind of stay in line with. So we gave them all a scale. So in this case, our cost and size, we gave them a weight of 3. So those were our 2 most important aspects that we wanted to focus on the most. Followed by weight, ergonomics, and time, given a weight of 2. And maintenance, durability, and aesthetics were all given a weight of 1. So they were all important, but we just felt that cost and size were the 2 most important. So throughout this entire process, we were in contact with many different experts. These are just 2 of the couple that we found. And first one was Ben Fleischman. He was an engineer, and he said, you may want to think about how much impact the UV bulb will have on your primary goal of reducing bacteria if it only shines in the back of the towel. So once he said that, we had to come up with a solution. So what we did was we painted the inside of our cabinet chrome, thus the UV light would reflect off of and come in contact with all parts of the towel. Another expert that we came in contact to was Chuck Krogh, and he said the environment created by the exhaust fan and the antibacterial appeal of the UV light seems like a very sound idea. So we just wanted to add that into our presentation to show that actual engineers and experts were in favor of our idea. So the next thing we have here is our working drawing. This was our first set of working drawings. This was the cover page for it. As you can see, this is an explosion view, and it just represents our box in the main portion there. And then we have 2 UV lights on the sides, which we later brought that down to 1 to reduce cost. And also you can see on balloon 3 there, that was our original casing for our heat lamp, which we later scrapped and we went to a heat pad to make it more user-friendly and to overall work better. So here's what we have for CAD design. This is just an isometric view here on the left, and here's just a front-facing view on the right. This was done in Autodesk Inventor. It's the software that we use here at Twin Valley all the time. Here's just two more views. The one on the left here, it's a 3D printed file, and we just wanted to show that just to give a better view of our 3D model. And then on the right here is our door. We actually later cut this out on the plasma cutter, so we figured this would be a good piece to show. So why did we choose this design? We choose this design for a couple reasons. Some of the main ones are it's mounted in the wall instead of attached to the wall. So to reduce it sticking out so far in your bathroom, to make it more ergonomically pleasing, we set it in the wall so it's flush with the back of the studs on the back side of the wall. We also liked it because it was a large single door and user-friendly. So those two things kind of go hand in hand. Having the large single door, you're able to open it up easily, and you are able to put your towel in it, and you won't cut yourself, you won't bang your hands on anything, it just makes it nice and easy. We also liked it because it allows for just a heated towel. So on the side of our box, it's the switch. So the switch can either be turned upright, and it will result in the UV lights, the exhaust fan, and the heat pad all coming on, or you can flip it down and just the heat pad will come on. And this was just a aspect that we like to add for comfort. If it's maybe cold in your house and you wanted a nice warm towel, it would just give you that, it would give the user just another reason to use it.
All right, hello again. My name is Aaron Crum, and I'll be going over the construction phases of a prototype. So once we were done with the CAD model, we decided to do a 3D printed model of our prototype to get a better understanding of how it's going to look and where things were going to go inside. So to the left, you can see that it's printing out, our model's printing out. And to the right, you can see that we were having some difficulties getting it to print right. This is because since the sheet metal was so thin to begin with, when we scaled it down, the 3D printer wasn't able to print that thickness. So we decided to scrap the overall idea, and we moved on to a cardboard prototype. So the cardboard prototype helped us out a lot. It gave us a feel for how big it was actually going to be, and like where things were essentially going to go on the inside. To the left, you can see we actually put a towel in it, and at this point, we were actually pretty happy with how it looked and how things fit in it. While constructing this, we actually used all the same machinery and equipment that we were going to use to do the real thing, just to familiarize ourselves with the equipment. So after we were done the cardboard prototype, we decided to do some incremental testing on our parts that we ordered to make sure that they all worked and did what we needed them to do. Here's a short video of us testing out the fan to make sure it did what it does. Next, so before we started to do any construction on the actual prototype, we decided to do a tool tray, sheet metal tool tray, to get ourselves used to sheet metal, because none of us have ever used sheet metal before. So we wanted to know how to cut it, how to fold it, and all that kind of stuff, because we've never used anything. So once we were done this, we felt confident enough to start a prototype. So our first cut went really well. Everything worked out great. But our second cut, our piece ended up being too big for the break in our school. So that's where Jelks comes in play. We want to give a big thanks out to Jelks because they helped us out a lot, and it was a great experience to go out and see like all the equipment and like see what they do and how they do it. They were able to cut the bigger pieces that we needed because they had bigger machinery. So they weren't able to cut out the hole for the door or the fan or the vents. So because they didn't have the right machinery. So we took it back, and to the left, and the right, there's pictures of us using the notcher in our classroom to cut out everything we could on the outside for folding. And so once we've done that, we used the plasma cutter in our classroom to cut out the door and the vents. And here's a video of plasma cutter. So the reason we used the plasma cutter was because it was way more efficient and accurate than what we could do, and plus we didn't have the right machinery in our classroom to do it otherwise. So there it's cutting out the vent holes, and there it's cutting out the fan, the hole for the fan. All right, so to the left, there's a picture of it after it was done with the plasma cutter. There's a fan hole, and that's for the door, and the vents are back there. To the right, this is for the timer. We didn't feel that it was necessary to use the plasma cutter for that, so we just used the hole puncher in our classroom to punch out that, and you don't see that, it gets covered up. So.
I'm Gavin Willach again. Before we put together our final product, we decided to paint the inside, like Ben said, a chrome color so it would reflect all the UV lights back to the towel and just help clean our the towel as much as possible. And then, so the picture on the left is the prototype before it's painted, and the one on the right is after. We went with a white, slim, sleek look so that it would flow easily with the aesthetics of almost any bathroom that it could be put into. And then, so these are constructions. This was after we were done painting. We used a machine called a spot welder to put the door onto our front piece. The spot welder, it is a welding device that heats up two pieces of metal, and when applied with pressure with your foot, it makes a solid mold between those two pieces of metal. And then this was just another way that we put our box together. Because the spot welder couldn't fit in all of the certain spots, we had to use rivets, which is bolts that held the two pieces of sheet metal together, which held the back part and the front part together. And that was just us punching the holes all along this side right here to put rivets in.
So the next part of construction was the electrical construction. So this was the planning period that we went into before we started just soldering wires together. So on the left here, you can see our calculations. So that was basically just using Watt's law to determine the total current. And we did that in order to determine we had the proper wire gauge and that all the components would have sufficient electrical power. And on the right here is our schematic for our design of our circuit. As you can see, that's the on-off-on switch mentioned earlier, the timer here, and then these are our different components that we did in order to, have the different settings that we mentioned earlier. So this is the first step of electrical construction. We were just using wire nuts to make sure that all of the schematic was correct and that everything would line up the way that we wanted to. This was before we obviously soldered everything for the final design. And then kind of a challenge in this electrical construction was that the heating pad that we ordered had a user interface itself, and that's this circuit board here. And originally in our designs, we thought that it wouldn't lead to any problems. However, when we toggle between the on-off-on switch position, the circuit board cut off the heat pad, so it wouldn't work the way that we wanted to. So we spent probably like 4 hours running tests, checking the amps, everything that you could imagine, to figure out whether or not we could simply remove that circuit board. And in the end, after we unsoldered everything from the circuit board and soldered those wires together, we found that if we simply connected the wires and removed the circuit board, then it would work the way that we wanted to. And on the right here, that's us making sure that the heating pad doesn't overheat and that everything works the way that we want it to. So after we completed the prototype, we obviously had to test to make sure that it was okay. So the first set of tests we did were our dimensional analysis tests. And that was basically measuring the height and width of the towel, the height and width of the prototype, and then finally how far the prototype sticks out from the wall. And we wanted those to fit our design specifications, and we also wanted to make sure that no matter how someone configures that towel, it will fit inside our prototype. And the next set of testing was arguably the most important, leading back to the problem statement. This was the bacteria analysis. So in order to do this, we did a 6 by 6 inch square on each towel in different positions. We had 5 different samples, and we used a clean cotton swab to swab out the square, and then we cut that cotton swab into a test tube filled with distilled and sanitized water. And then we put that towel into our prototype for 30 minutes, and we came back, took it out, swabbed the same area, and cut that into a similar test tube. So then we took the samples of that and we put it on a Petri film specially designed to grow coliform and E. coli bacteria. And after allowing those to culture for 48 hours, we found that one of our samples, which makes sense, 25% out of 5 samples, one of our samples had E. coli bacteria. And obviously it's only one colony, and that may have been because our test tube dilutions were way too high. We did upwards of 6,000% because we weren't sure how much bacteria would be present. But after running the cultures, and this was the before and after, we found that all the bacteria was removed, so we deemed that a success. And our final steps of testing were what we called the general tests, which consists of 3 separate ones, which were the integration test. How well does it fit inside the bathroom environment? The UV bulb test, how easy is it to replace the UV bulb? And finally, the general usability test. So this here is simply a video of one of our classmates going through the prototype, using it, and then after he goes through this, taking the towel in, putting it out, trying it, he filled out a small half sheet just to give us information on how easy were the different steps, how hard were they. So it's just a video. This is obviously just testing the UV bulb, seeing how easy it is to put in, take out. That's what we deemed as our maintenance test. So that's how we gathered our data for those sets of tests. This is our final analysis just of the numerical values. As you can see on the right-hand column, all of our tests passed except our weight test. Our goal was 20.5 pounds, and the actual result was 25 pounds. And then, of course, the bacteria test, although it was one reduction, as I stated earlier, that reduction obviously resulted in 100%. So, yeah, every other test passed, the dimensional analysis and the general testing.
This is a cost analysis we put together to show our total cost for our prototype, and our overall cost was $136.04. And the left side of the chart right here shows the components and the quantities of each component that we used. And then on the right side, we showed how much each one costed. And the middle columns were the description of what each one was and then where we purchased each product. And then this was a question from our survey. We asked how much would you be willing to pay for this product, which was a towel cleaner, and in the blue it is a 72.7%. People said less than $50. And then in conclusion, we said from our project we concluded if we were to change anything, it would be we would start the construction process earlier, so we could focus on attention to detail and how much detail we put into each component and the overall prototype. And we also said we would use different materials instead of sheet metal, maybe something lighter so we could come more closer to our goal of 20 pounds instead of 25. And overall, that might just reduce the cost as well. And another thing that we wanted to do was put insulation behind the heating pad so that the heat would be kind of kept back into the enclosure and make a warmer towel. And then a reflection of what we learned, see what we could do better next time and what we did well this time and what we would do differently next time. And then throughout the entire semester, we were problem solving as a team, doing all sorts of things as meeting deadlines as a team. So that just really, problem solving and working with the team was probably one of the biggest things that we worked through. And we also learned new skills as well as soldering different wires together, as Evan explained. We had to wire out that whole circuit board and then we realized we didn't even need it. And then just sheet metal individually, folding, welding, riveting, putting holes, punching holes. Was just an all-over experience that we got to go through. And then we would just like to thank everyone that helped us through the process and through the whole semester. Jelks Fabrication, Mr. Joy, Mr. Bowman, and then all the experts that contacted us and responded to us. Chuck Krog, Ben Fleischman, and Todd Moyer. That's it. Thank you.
Thank you again for coming to our presentation. We are Team Visionary, and we have created the thermal bag. My name is John Wadnick. This is Sarah Diamond, Ruth Jacob, Grace Brennick, and Jeremy Kovalevsky. Throughout this semester, we had to follow the engineering design process. So we had to come up with a problem. We had to generate the solutions for this problem. We had to develop and test a new solution. We had to construct a prototype, and at the end, we had to evaluate the process as a whole. This here is our Gantt chart, and it was essentially a timeline that kept track of the problems that we would come across. Everything in blue are milestones, such as actually coming up with the problem or finishing the prototype. So obviously the first step was to come up with a problem. As a team, we had to decide on a problem that we would all like and would like to follow. This here is a list of our top 10 problems. The items listed in red were the top 3. Obviously the sleeping bag won out, but the other 3 for condensation covering car windows and the end of cords breaking easily were heavily considered. And these decisions were based off of this matrix here. And we had a list of criteria that we weighted differently. So we based it off of if the problem could be accomplished in the given time, if the problem was interesting enough to keep the team interested, and if the solution was able to produce a prototype. So idea 3 is the sleeping bag, and it won by over 10 points, so we chose that problem. So our official problem statement, we felt that temperature range in sleeping bags is inadequate. There's no sleeping bag on the market with the capability to stay warm in winter and stay cool during the summer. After the team came up with this statement, we had to justify the problem. To accomplish this, we sent out surveys to the staff here at Twin Valley, some camping forums online, as well as our personal social medias. Our first question was, how many sleeping bags do you own? 75% of people said they own more than one sleeping bag, so this helped in aiding our justification. The second question was if users felt like sleeping bags were poor at controlling temperature. And a majority said yes, sleeping bags were poor at controlling temperature, about 60%. Of those who agreed, we asked them for their reasoning. Majority of them said that they are either too hot or too cold, thus confirming our problem statement. And here's just a zoom in of some of what people say.
Hi again, I'm Sarah. So our next project phase, generating solution concepts, was heavily focused on brainstorming ideas for a solution to our problem after researching what products already exist. For this similar product assignment, we researched items that already exist that could potentially solve our problem. The first patent on the left was a vented sleeping bag that utilized multiple layers to regulate temperature. From our market research, we found that some people get up in the middle of the night to unzip their sleeping bags, disrupting their sleep. We still liked the idea of vents, however, we put them within arm's reach so the user wouldn't have to get all the way up in order to get airflow throughout their bag. The second patent on the right was an electronically heated sleeping bag. As you can see, it's a very bulky design, so we decided to innovate it by creating a more compact design, especially in terms of the battery size. We also referenced this patent's heating coil schematic to see how to evenly heat the bag. However, we used 2 strips of carbon tape rather than just one long line. As you can see there, they have their heating coils going all the way around. We have our split. This is our similar solution matrix where we rated 5 existing products and patents based on these specifications. Our most important specifications, we wanted it to stay warm during the winter and we wanted it to be battery powered. The higher the product was rated was what we wanted our product to be most similar to. So this air mattress sleeping bag was our top rated product. It's basically just a sleeping bag with an air mattress on the bottom, so when it's inflated, the user would be off the ground. However, our product was actually most similar to the Western Mountaineering sleeping bag. After all that research, individually, we created a dozen sketches of what we wanted our final solution to look like. This first sketch on the left was a pair of one-size-fits-all heated pajamas with wires running through it, similar to a heated jacket. And it also features vents on the side, so you could still have airflow through the bag if you got too warm. The second sketch on the right is a removable liner, heated liner that is charged by solar panels. So during the day, you could charge it in the sun while you're on your camping trip, and at night, you could heat it up just before you go to bed. Both of these sketches we thought were good ideas because you could already use them in the existing sleeping bag you have rather than going out and buying a completely new sleeping bag.
Hi, my name is Ruth, and in this section I'm going to discuss the next step of our product, which is developing a testable solution. At this point, we have already identified that we want a bag as opposed to a different idea, so in this section we're going to go over some of those ideas that we went through after discovering that. So first was our mind map. We used 2 different mind maps specifically. This one was for non-powered solutions, and the next one, which I will show, is for powered solutions. So we use this as a team to map out our ideas. We have different concepts identified, such as these 2 up here. This is for a flippable layer. One side would be cool, one side would be warm. Down here is outlining the need for airflow to create that cooling. Over here, this is comfort and packability, which we found is very important to consumers. And that's just that. Here's a blow up of that comfort section, just showing some of the ideas we went through. Like this is a liner to go underneath. This is sort of a different padding mechanisms. There's a pillow, stuff like that. So these are some of our powered solutions, which we inevitably went most with. So we had both cooling and heating solutions to create that power, one of which was the heating coils, which was went over earlier. And this one over here, which we didn't quite go with, had fans on the outside that would point towards the user. So for design specifications, we used patents earlier to identify some of the important points that we wanted to use for our final prototype. So we found that comfort was very important, which I have already said. Performance is also very important, especially with a powered bag. So we wanted battery life to last at least 10 hours. And we also wanted it to withstand cold and hot temperatures, specifically between 0 and 90 degrees. So durability and maintenance, we found that since we were having a powered solution, it would be difficult to wash the bag and to keep it clean. So we wanted a removable liner that would separate the user from the heating elements so that you could wash it and keep the bag clean. So for material, we used the design specifications that we had to distinguish the materials that we needed, specifically to withstand high temperatures. One that we identified was fleece, which is pictured right there. We used a black fleece for our bag to help retain the heat. And another which was a wicking nylon on the outside, which would separate any sort of weather, any sort of dew on the ground. And we wanted the materials to be easily workable so that we could maneuver them the way that we wanted. So after identifying all of that, we had some concept sketches that we went over, specifically to identify what we really wanted to use. We used a little bit of both ideas from powered and non-powered So this was just outlining one of the non-powered solutions, which was the liner. This was what we most likely went with more. It had the heating coils up to the middle. We had the battery on the bottom. We actually moved the battery from the bottom to our side for the final prototype. And after all that was said and done, we needed to create a plan for when we actually created the prototype. So this is just the front view of our working drawings. We have all of the layers individually spaced. We have the wicking layer, 2 fleece layers. You can't really see the heating elements between that. And then there's insulation for comfort and the nylon layer on the outside, as well as the batteries and other. So throughout all of these processes, we contacted experts to give us feedback and to help us, specifically 2 Twin Valley alumni, which is Jeremy Ott and Daniel Techman, which helped us in identifying what components we should use and giving us different heated solutions using energy. And another one was Feathered Friends, which is a camping gear company stationed in Seattle, Washington. They gave us a lot of feedback, specifically on sleeping bags, which the other 2 experts could not give us. They specifically referenced some of their own products to help us with our own, and so that was a lot of help. Here are just some examples of correspondence, just to show some of the feedback that they gave. They identified that packability might be an issue because of our battery. It might be a little bulky, specifically referencing some of the other patents that we looked at. Bulkiness was definitely an issue, so they just sort of identified that we should focus on. And then finally, STEM concepts that we had to look forward to using being in EDD. Material science to identify what fabric we wanted to use. Definitely electrical circuits, which we use for our heating elements. We used CAD to create our working drawing, specifically Autodesk Inventor. 3D printer when we created our model, which is not pictured, but we had 2 different versions of our model, one of which was an assembly, which had all the layers compacted together to see how it was, and then we did another one which each layer individually spaced, as well as a sewing machine for our final. For math, we used a lot of calculations for determining wattage and what kind of battery we wanted to use. Here's an example of those calculations. This specifically shows runtime and what kind of battery we want to use. So we identified the runtime as, I think, 2.5 hours. That was early in our planning, so I think it was adjusted since then.
Hi, my name is Grace Brennick, and I'll be talking about our construction and developing our testing. This section contains our project planning, fabrication, and our testing procedures, and a reflection of our testing. Our project planning contains most of the items we use. However, some items, considering a battery, had to be ordered outside of this list because we misunderstood some of our electrical requirements. The fabrication included fabric preparation, the different layers of the bag, there are 5 in total, a vent system, and wiring the switch box. So for the fabric preparation, we cut and hemmed each of the pieces of fabric so they would meet our specifications. The bag contains 5 separate layers. The outer layer is a ripstop nylon. This is waterproof. We have a 1/2-inch polyester batting. There are 2 layers of fleece. These sandwich the heating coils to give them more insulation. And a thin cotton sheet, which isn't pictured, that is the wicking layer. This was removable. Later, once we finished adding the layers together, we added vents that are in arm's reach, so that way the person does not have to get out of their sleeping bag to add ventilation. And then Jeremy will talk about how we wired our bag.
Hello, I'm Jeremy Kowaleski, and I will be reviewing some of the electronic components of our sleeping bag. So right here, this is a picture of our circuit diagram. Right here is our battery, and initially we were going to have a high and low setting for our bag. So up here you see 3 resistors that we had in class. That would be our high setting because of the higher ohm rating, and the bottom would be the lower ohm rating. And right here would be the heating coils for our bag, and the length that we had them were 40 ohms initially, and then it would just go back to ground. Though we had to change it. So right here, this is our final circuit diagram. That's our battery. We have an on and off switch for the main thing, and we went we wired one to ground, and then the one went to our heating coils. We switched over to 2 heating coils instead of 3 to make a better heating solution to get it warmer. So working with the heating coils, right here, that's a picture of the carbon tape that we use to heat the sleeping bag. So with that picture, we flow current 12 volts through the wire, and with that length of wire, it gets warmer. And we also tested that circuit outside, and it got up to about 63 degrees that day outside. And that day, I believe it was 20 degrees outside. So personally, I feel like that's pretty impressive. And that's a picture of the digital multimeter used to test the ohms of our circuit. Now right here is a picture of us attaching the heating coils together because the Amazon order that we had did not have the proper length for us. So here's the video. We have silver glue, which is this electrical component that we use to attach each of the components of the carbon tape together, as well as the digital multimeter and us actually sewing wires into the carbon tape. Now this is me working on the switch box, which has the on and off switch mentioned earlier from the circuit diagram. That's me wiring the input for the battery, and this right here is the assembly of the box. Right here, this is the acrylic weld that we use to weld each of the pieces together to make a box on the edge of our prototype. This again is us wiring the solution this is us wiring the wire into the heating coils so that we can have proper heat. Yeah.
Here's another picture of the wiring in our test box. This video shows the construction of the bag. So the video starts off, we're hemming the outer ripstop nylon layer. And here's the whole sheet completed. Its dimensions were 50 inches by 72. Then we cut the 1/2-inch polyester batting. It's actually cut a little bit shorter, so that way you're able to attach the fleece over it, so that way it would fit. After that was done, we began to work on the two fleece layers. One of them was attached to the nylon in order to create a pocket that we could slip the batting into. The vents were added after this was completed. And then we are hammering snaps into the wicking layer to attach it to the fleece. And then our bag was completed. So we came up with both qualitative and quantitative tests for the effectiveness of our bag: temperature, aesthetic appeal, battery life, comfortability, and a general questionnaire type questions to see how likely consumers were to buy our product. To ensure that our prototype accomplished all of these, each team member created testing procedures to determine the functionality of each aspect of our project. One of the first tests we ran was the battery life test. The battery ended up running for over 10 hours, so we said it passed with about flying colors. The next test procedure we did was comfort. This test also passed because we had an average of around 4 for each answer. The next test we did was temperature. We decided that this test needed to be stabilized. So the temperature before the bag was turned on was about 47 degrees, and it stabilized at 75. The last test we did was weight. Unfortunately, our bag failed this test. We expected our bag to be about 7 pounds, but it was over by 2 at 9 pounds. The last test we did was the color material test. We simply wanted to ask the consumer if it was pleasing to their eye and if the materials felt nice. So the reflection of our testing, we decided that the bag was a success. It was comfortable and it was warm.
Hello again, I'm Jeremy, and in this section I will be evaluating our solution as well as the process used to solve our problem. As every group encounters, our team had struggles, but ultimately we got the product finished, And some of the problems we encountered were teamwork-wise, as well as completing our prototype on time. Though we learned a lot of new skills along the way. So some of the big picture ideas that we learned were about soldering, fabrication techniques such as sewing and hemming, and general knowledge such as project planning and teamwork from this class. So an overview of our product. Due to the many successes of our product through testing, as well as the problem's notoriety as an issue many campers had, I feel that our project was a success. For a closing statement, reflecting on our process and product, it turned out very well. And as I said before, I generally believe that it was a success, but there were flaws in it, such as the weight test. A couple things I would change throughout the process is the cooling solution, because we only had vents, and initially we were going to have a better cooling solution, but vents also provide other ways of cooling besides just cool air. And we also wanted to spend more time on our prototype so that we could make a better prototype and pay more attention to detail within our bag. And we would like to acknowledge our experts and supporters throughout the process. Guide helped us with, learning about the heating coils and technology, and ultimately that's how we decided on the carbon tape. Feathered Friends helped us with the camping gear and the sleeping bag in general. Mr. Joy, he taught the class, and Daniel Techman, Jeremy Ott emailed us quite a bit on working out the design and electrical knowledge that we needed. And we would also like to thank the technology department for helping us no matter what we needed, if it was just a simple electrical component or if it was like learning a new technique to make the bag. They were there to help. Thank you.
Hello, my name's Elijah Rivera. Next to me I have Max Hafer, Brandon Ward, and Gavin Kane. Together we make up Phoenix Engineering, and the product we designed this year was the Performance Prop Guard. To start the course, we came in with about 200 possible ideas that we could pursue. We were able to narrow down the problems to sea turtles being injured by boat strikes. Throughout the course of the problem statement evolved based upon new information found, different ideas, and expert feedback. Once we were set on our concept, we finalized our problem statement to the one shown, which is its main idea is to protect wildlife while not sacrificing the boat motor's performance. To start the semester, we were given a Gantt chart that outlined the entire course, and this Gantt chart changed over time as we fell behind some tasks or got ahead of other tasks. To start our project, we first had to prove that our problem was actually relevant. So we made a survey, and we researched different marine wildlife hospitals, rescue centers, and different marine wildlife websites. We sent them our survey, and two of the questions we asked them were how many injured marine animals have you seen in your lifetime, as well as if there was an item on the market to help limit the destruction of marine wildlife, would you consider buying it? The overwhelming majority said yes to our survey. This showed that there was indeed a problem with boat motor strikes to marine wildlife, and also that a lot of people would consider buying a product that would help protect them. While we were waiting for the survey results to come back, we began doing academic research of our own. By reading this article and many like it, it became very clear that boat strikes is a major problem all over the world. And in this case, the Australian government had to put regulations on boats because of all the boat strikes that were happening. Other articles stated that boat strikes have tripled in the past 40 years, as well as in 2016, 5 sea turtles were found in as many weeks. They say the sharp increase of collisions is directly correlated to the amount of boats in the water. To get ideas for our product that we wanted to make, we researched existing products on the market. These were 2 of the options: Max River Runner Prop Protector. We found that its main purpose was to protect the prop rather than to protect it from wildlife. And then the Propeller Guard Red, 14 inches red. It covered the entire prop and would protect animals, but in turn would affect performance greatly. Our aim was to protect the wildlife while minimizing the effect that it would have on the boat motor. We also found patents that were already existing. Most had not been sold openly on the market. And again, we found that they were either covered in a way that would drastically affect the performance of the boat motor or in a way that would not sufficiently protect the animals. Once we found a couple of designs and solutions, we put them in a decision matrix, and we rated them on a scale of 1 to 3. We found that the Propeller Guard Red 13 or 14 inches was the best one. It still had some flaws, and the main one being the price.
So the design specifications were just a series of criteria that we wanted our final solution to follow. Our most performance criteria was performance. We wanted the product to be able to protect wildlife without sacrificing any of the boat's performance capabilities. Second is materials. The guard must be durable and able to withstand speeds up to 30 miles per hour in water. Third is customer needs. The prop should function so that the boat owner hardly realizes it's there. Fourth is size and weight. The prop should fit on any outboard boat motor, and its weight should not impact the boat's performance. The total cost of the prop should be under $150, so it's reasonably affordable for the average boat owner. And the prop should be simple and easy to install on any outboard motor. So the mind map allowed us to brainstorm our ideas onto paper and put some classification to it. Our first mind map, which you can see right there, was just a series of wires that would attach between each propeller blade. And Elijah, one of our group members, is holding one of our mind maps. Our second mind map was sort of like a fish finder for the boat. It would detect if there's an animal coming and then shut off the motor and bring the boat to a stop.
All right, I'm Brandon. So after the mind maps, we made concepts that we would actually be able to make and test. So the first type, we used the sonar or fish finder technology that would shut off the motor if an animal was detected. Our second type of concept was to make a safer propeller rather than a guard. And so here we had wires connecting each of the blade, and that would minimize the chopping effect that it had if it would hit an animal. And our other type was, it used sonar, but it had moving parts. So here, when it would detect an animal, 2 flaps would come down, and the motor would shut off, and the flaps would be like brakes for the boat, and it would drastically reduce the speed, so it would minimize the collision with an animal. All right, after we had made all of our concepts, we put them all in a matrix to determine which one was the best. And to do this, we used criteria such as how testable it would be, the cost to make and sell it, and how well it fit with our problem statement. And so the final concept we decided to go with uses a stepper motor to use a metal guard in and out of position so that when you need it, the propeller will be protected, but when you don't, it won't negatively affect the performance of the boat.
Okay, we were able to get in contact with an expert early on in the course. His name is Peter Keller, and he's a boat strike coordinator for NOAA. It's a government agency that researches the atmosphere and the ocean. He was able to give us important facts about what happens when a sea life comes in contact with a boat, what types of boat do the most damage, as well as where most boat strikes occur, and what can prevent their deaths. He was able to tell us that most boat strikes do in fact occur on inshore waters due to high concentration of marine wildlife. He was also able to give us feedback on our concept sketches, the one that were just previously shown. He gave us also some more information and research that we missed. Once we finished our 3D model in Inventor, we sent him isometric views of the guard. He was able to tell us that the placement of the guard is extremely important, and although the drag is almost impossible to remove when using a prop guard, being able to move it out of the way would minimize the effect on the motor. We also had another expert, Tyler Legal, who gave us some feedback on our 3D model, as well as some advice for construction.
So these are a few of our strength calculations for the boat motor. We use these to determine what size stepper motor we should get and how much power it would need. As you can see, we made a whole series of calculations here, but upon consulting with Mr. Joy and Mr. Ott, we decided this was the formula we would go with.
All right, so my name is Gavin Kane, and I'm going to be talking with you guys about the 3D CAD modeling process. So what we did is we basically went into Inventor and created multiple different parts and then put them together inside of, as you can see on the left, inside of this explosion view, and we put it together, and once it was all together, we could move the prop in and out of position to make sure that it would function correctly in real life. And here's a video showing that. And what this basically did is allowed us to see that it would move and function as we desired. All right, so this is another part of the 3D CAD modeling process. So these are our working drawings. So each part that we developed, we had to make a set of drawings for it. That way when we were fabricating our parts in real life, it would make it easier for us to create them because we had basically a template in front of us to work off of.
This is our 3D printed model. We made this to just make sure our boat would look and function the way we planned. We printed it in quarter scale, obviously, because it's way too big to print full scale. And here's a video showing our teammate Brandon moving it into position. So as you can see, our 3D printed model works exactly as we hoped. And we had the telescoping feature, which allows it to fit other types of motors. In these pictures, we have constructed our circuit here. That's the box that holds all the switches, the Arduino, the motor driver, and here's our 12-volt battery. We also have some of the code here, which controls the Arduino and moves it into position. It spun the motor 180 degrees. That way it wouldn't hit the motor or the boat. And it also has a feature so you can't toggle the switch the same way and end up damaging the boat or the prop. In these pictures, you just get a better view of what our circuit looks like. We made a box out of plexiglass, and it has some holes in there to allow the motor driver to vent and cool. And here are a few of our electronics. You just get a closer view of the way our stepper motor is mounted for the prop guard, the way our Arduino is hooked up. And our stepper motor spun 180 degrees, and this just allowed it to function and cover the prop correctly.
All right, so I'm going to speak with you today about the construction phase of our prototype. So in this picture right here, I am deconstructing a boat motor that we got donated from a marine shop in Lancaster. And it actually took us a couple days because this piece right here has a shaft that runs all the way down to where the prop is, and it took us a little while to figure out how to disconnect that without damaging the rest of the boat motor. All right, so this part is the tube bending. So as you can see with that arrow pointer on the screen right there, this is the part that we are making right there. And we needed this steel tubing to have a bend in it. So what we used is we used that machine that I just played the video of to slowly increment and bend it. And we used, once again, the working drawing to check the angle and make sure that it was bent at the correct position that we needed it to be bent at. All right, so this is the construction of our telescope tubing, which we use the mill for. So this is an inventor drawing. It's a program called HSM, which allows you to run a simulation of what the CNC mill will do, and then once you do the simulation and it works properly, you can generate code, which will then be sent to this right here, which is our CNC mill that we have at our school, and it will run exactly how it's programmed, and with 100% accuracy construct your parts. So we used it that way we didn't have to worry about holes being misplaced or anything going wrong with our construction. And right there, you can see that is where this piece ended up going on our final prototype. So this is the construction of our tubing. So our